Oh, yeah. The video starts recording at 5 minutes after the hour, so that's why
Speak for this. Hello.
Today we started with a brief presentation from Kenji, the leader of the RoboCup team. He's going to tell you a little bit about RoboCup.
Hi. I just want a quick show of hands. How many people know what RoboCup is? I just want to make sure. Okay, not many. So RoboCup is an international competition about autonomous robot soccer. It's 5 versus 5 robot soccer where no one controls the robots during the game and they have to play a 20-minute game against other countries. This year we're doing our recruitment period next week. If anyone is willing to join, on the team we have a mixture of undergraduate, postgraduates and alumni, helping from the industry as well. And we're going to be running our recruiting period next week. So if anyone's interested, please take a photo of the screen right now. It'll be a quick Google form about how experienced you are. It is a research project, and it can be used as industrial training and also as a thesis project or a research project under computer science. I think that's about it. Yeah, so this will be running in the Ainsworth building on level 5. Maybe some people have seen the soccer field there. But please fill out the form first. You'll need experience in C++ or Python. And hopefully see you there. Thank you. Sweet.
We'll be in touch about the mask.
Yeah.
Oh, yeah, of course. Good. Okay. So, as you probably know, we had a bit of a problem with the lecture recording last week. I'm told it's because I use HDMI connector instead of the VGA. So in future I'll use the VGA with my laptop, but it might be safer when we have the slides just to use the internal computer. So as I mentioned, this is the course website, and the lectures for the first 3 weeks were posted here, and then I've also added a couple of quizzes and exercises. So have a go at these little quizzes and exercises in your own time, and I'll be adding, releasing solutions. There's links to the solutions. They'll be posted a week after the quizzes or so as we go along. So it's good to have a bit of time to have a go at them yourselves before we post the solutions. And I might also mention that we've just the consultation times. So the ones at the moment we just have the Tuesday 2 to 3 consultation running, but when we get to weeks 5 and 6, we'll have these other ones running to help you with the assignment. We're still working on the assignment. We're going to release it by the end of next week, but Alex, the course administrator, has put a notice up on the website just reminding you that it's a good idea to work through some of these, to install TensorFlow, install PyTorch on your machine, and maybe have a look at some of these resources if you need to, just in preparation. Good. So today we're going to talk about backpropagation. So we'll start with supervised learning. I'll talk about Occam's razor. Then we'll look at having multi-layer networks and continuous activation functions and gradient descent and backpropagation. And then later on, or the second half, we'll talk a little bit more detail about various. First of all, about some probability that we're going to need for this course, and then about some variations on the basic backpropagation algorithm. So there's 3 types of learning that we're actually going to talk about in this course. There's supervised learning, reinforcement learning, and unsupervised learning. So we're going to start with supervised learning. This is where an agent is presented with examples of inputs and target outputs to learn, and then it has to try to, after it's trained, then it is presented with a new set of inputs that were previously hidden, and it has to try to guess what the outputs should be for those new inputs. So this is supervised learning. That's what we're going to be talking about for the probably first 5 weeks of the course or so. Then we'll have probably 1 week on reinforcement learning, and after that look at some unsupervised learning methods. So with reinforcement learning, the agent is not presented with target outputs, but is given a reward signal which it aims to maximize. So we'll look at examples of trying to learn to play Atari games like Pong using neural networks, or sort of simulated physical environments. And finally, unsupervised learning. In unsupervised learning, the agent isn't given target outputs, it's only given inputs, but the aim is to kind of try to find some structure from those inputs. So we'll talk more about those things later on, but for the moment we just concentrate on the supervised learning. Now, right, so with supervised learning we have a training set and we have a test set, each consisting of various items. And for each item we have a number of input attributes, and then we have a target value which is specified. And the aim, as I said, is to predict the target value based on the input attributes. And so the agent is presented with the input and target outputs for each item in the training set, and must predict the output for each item in the test set. Yeah, so there's always, those of you who've taken the machine learning course will understand there's always this kind of strict demarcation between the training set and the test set. And if you're going to do supervised learning, you have to choose well, you have to make various choices, but the first choice you have to make is the learning paradigm. Now, in this course, obviously, we're going to be using neural networks, but it's good to be aware that there are other paradigms available. So decision trees, support vector machines, k-nearest neighbor, and so on. And so that's the first choice of the type of framework. Well, then you may have to choose a representation for the inputs and the outputs. So depending on the task, the choice of representation may make it easier for the task to be learned. If you choose a more kind of natural representation, you might have to do some pre-processing of the inputs, rescaling or manipulation of the data somehow, and also post-processing. So post-processing means just anything you do after you get the output from the network. Then you've got to choose a training method. So we talked about perceptron learning. Today we're going to talk about backpropagation. There's other optimization algorithms. There's conjugate gradients and various other things, and there's parameters that you can adjust. There's the issue of generalization and avoiding overfitting, which we'll talk about in a minute. And finally, evaluation. So often the evaluation is just simply like the accuracy on the test set, but depending on the purpose of the system, you may want to evaluate it in a different way. So, for example, if you're training a neural network to do stock market trading, the output would be interpreted as whether to buy, sell, or hold particular stock or bonds. And so you can, so if we look, and then what you're trying to predict, probably it depends on if you're trading, you know, from one day to the next. For example, then, I mean, people don't do this anymore because they do the high frequency trading. But let's say typically you buy stocks one day and maybe sell them the next day. So the classification would be whether that stock went up the next day or down the next day. So the accuracy would be based on that. You know, how many times that you thought it was going to go up and it did go up, or how many times you thought it was going to go down and it did go down. But really, what you really want to know is whether you would make money if you use that network. So often you would set up a system where you train the network, and then you know, let's say you set aside, you have all this historical data, and you set aside a certain time period in which you train the network, and then you set aside a later time period for testing, and you want to say, okay, well, what if I had trained the network up to this point and then started actually trading based on the recommendations of the network, how much money would I have won or lost under that scenario? So it translates it into something tangible, because that's really ultimately what you're interested in, is whether you're going to make money or not, rather than the accuracy is just kind of a stand-in for that. So depending on the task, often there's this different kind of evaluation. And the same can be said with many other tasks. Autonomous driving, obviously the task is to drive along, to drive from one place to another without veering off the road and so on. So in the lead up to this sort of discussion about Occam's razor and generalization, so let's suppose you have a bunch of data. So this is a very simple scenario. You do a physics experiment where you have something that you can control and something that you measure. So I think I mentioned the possibility that you could dangle a pendulum, and so the variable on this axis might be the length of the pendulum, and the variable on the other axis might be the time that it takes to swing back and forward. Or you could drop weights. You could roll a little wheel down an inclined plane and measure the time and how long it takes to move a certain distance or whatever. Whatever it is, these various physics experiments that you may have done in high school, and you do various experiments and you plot them on a graph like this. And then the idea is we want to have a method of saying, so this fits into supervised learning, because we're saying, well, what we want to do is, if I give you another value here that wasn't tested, I want you to predict what value you would expect to measure. If x had this value, what would be the y value? So if it's within these points, it's like interpolation, and then if you go outside, it would be extrapolation. And you can try to model this with different models of increasing complexity. So this is a straight line, or in the second half today we'll talk more detail how to excuse me, how to fit a straight line to data. That's probably the best line that you can fit. Or you could fit a parabola, or a fourth order polynomial, or just some really kind of wild, crazy curve, right? So let's just go through this exercise again. Like, who thinks the straight line is the best choice? Who thinks the parabola? Yeah. Who thinks the fourth order polynomial? Who thinks the wild and crazy line? So again, it sounds stupid to say this, but philosophically, that line goes through all the points, so why shouldn't we choose it? Right? So the reason basically is that these other choices are simpler. This is the simplest model in some sense. It's only got 2 free parameters. This has 3 parameters, and this has 5 parameters. Okay. Now, let me just say, so most of you chose the parabola, but a few of you did choose the fourth order polynomial. And in a way, I mean, look, the yellow one's obviously too complex. That's no good. The red one, I think, is too simple. But the choice between the parabola and the quartic is both of them are right in a way. The people who chose the parabola and the people who chose the quartic, in a way, are both right. And it's well, we'll come back in a minute to explain what really the difference is between these two models. But somehow we want to find a compromise between complexity and how the complexity of a model and how well it fits the data. So this is this principle was popularized in the 14th century by William of Ockham, and so it's his nickname well, the nickname of William of Ockham himself was Ockham's razor at some point, but then in the 19th century, the phrase Ockham's razor became applied to the principle rather than the person. And it's kind of a nice metaphor, because we think of this as a razor, like a razor blade that's kind of cutting away unnecessary complexity from the model. And what William of Ockham said is that if you've got two models that both explain your observations, but one is simpler than the other, you should choose the simpler of the two models. So that was the original formulation. But in the modern era, we interpret it slightly more generally. We say that we're willing to accept a model that fits the data less well as long as it's more simple. So this is another example of kind of classification problems, or actually we were looking at this last week with the perceptrons. This data here can't be learned with a perceptron because it's not linearly separable, but the idea is to draw some kind of curve, ideally with the crosses on one side and the circles on the other. And if you draw something really simple like a straight line, you're going to get a lot of them wrong. If you're desperate to get all of them correct, then you have to draw, if you draw a kind of curve that weaves around quite a lot, then you can get all of them correct. But intuitively, we somehow feel that this thing in the middle is a good compromise. Like, it's pretty simple. It's not quite as simple as this, but it's fairly simple. It's looks like a bit like a hyperbola. It doesn't have as many kinks as this thing. And it gets two wrong. I think it gets one cross on this side and one O on that side. But we're kind of willing to accept that it makes some mistakes on the training data because we feel like it'll give better generalization, right? So the one on the right is considered to be overfitting. So these are the phrases that we use is overfitting and generalization. So this model here is considered, this is an inadequate model. This model here is considered to probably give good generalization. This one is overfitting to the data. It's kind of pandering too much to the details of the data and probably including the noise. Right? Now, let's just go back to this question about the quadratic and the quartic. Whether you choose the quadratic or the quartic really depends on how much you trust your data. So there's probably two different types of error that can occur in the data. So one source of error is noise in the measurement. If you're dangling the pendulum and measuring the time, the air resistance has an effect, and the friction in certain cases has an effect on the outcome. And then if you're timing it with a stopwatch, your reaction time can vary a little bit. So there's these sort of tiny little errors that add up to move the thing a little bit away from what it should be. And as I said, we'll go into more detail about that in the second half. Like if you add up a large number of if you add up a large number of independent variables, if you add up a large number of small independent variables, you always get a Gaussian distribution. But then you get these kind of really it's possible you can get these really crazy errors those are sort of microscopic errors in a way, but then you can get these kind of macroscopic errors where either the equipment has just malfunctioned and produced a completely erroneous value, or human error. Someone meant to write down someone's like writing down something or typing it into a keyboard and they meant to type in 96 and they accidentally typed in 69 or something. That can happen. So if we choose the green curve, what we're effectively saying is that we think that this is an outlier. We think that this point is really some sort of mistake. And so for that reason, we're not even going to bother to try to fit it into our model. If you choose the blue curve, then you believe that that point is really accurate. You're very confident that the data is accurate, and so you want to have your model go to some effort to try to include also that point, right? And so you have to make, in a way, a subjective judgment or a judgment based on what you know about the equipment and the problem domain and the the carefulness of the humans that you're working with, whether you think this is an outlier or not. So something that's really very far out like that is called an outlier. Right, and so this has an effect. And this is a famous example of an outlier. This was the 2000 presidential election in the United States, one of the closest elections in history. And George W. Bush won the election over Al Gore by, he won it by one state, which was Florida, and after many recounts, and I think the New York Times got hold of the votes and carefully recounted them later on, and the margin of victory was less than 1,000 votes. Some people say it was as low as 150 votes. And interestingly, like this graph shows every county in Florida, how many people were. There was a third-party candidate. They don't have preferential voting in America. They just add up the total number of votes, and there was like a third-party candidate here called Pat Buchanan. And this graph shows how many votes Pat Buchanan was predicted to get in each county based on exit polls and how many votes he actually got. And you see there's an outlier here. Like everything else is along this nice straight line. But somehow in Palm Beach, he managed to get 10, and this is a log-log scale. So he actually got 10, he got 100 times as many votes as what had been predicted. And so when you see something like this, whether it's in politics or whether it's in a physics experiment, you kind of scratch your head and try to look for some other explanation. And the explanation in this case is that the ballot was kind of poorly designed in that particular locality, and many people who wanted to vote for Al Gore accidentally voted for Pat Buchanan instead. So this is often how scientific advances are made, that people draw a graph and see something odd and then investigate further. Okay. Right, so that's supervised learning. Oh, sorry, I just mentioned, yeah. So what we're going to do, we probably won't. We'll get to it like at the end here, but with neural networks, the equivalent of the way we're going to talk later about how to avoid overfitting in neural networks. Yeah, so one way is to limit the size of the network, and there's various other ways. Okay, so now let's go back to what we were discussing last week. We were talking about the perceptron learning algorithm, and we looked at a few specific cases. So we showed how a perceptron could learn the AND function and the OR function. We have 0 is false and 1 is true, and we draw a little graph like this, and these things are linearly separable, and you can figure out the weights. And then we talked about the XOR function, and you can't have, it's not linearly separable, so you can't have a perceptron to do this. And we talked about how we could design by hand a network to compute XOR. So first we convert, first we take XOR and convert it into simpler logical terms, and then we make little perceptrons for each of these, and we connect them all together, and we get what was traditionally called a multi-layer perceptron, an MLP, and the whole thing computes XOR. And it's one of the exercises, among the exercises is that you will go through is to try to go through this process for other logical functions. So it turns out if I give you any logical function, you can actually build a two-layer neural network to compute that function. You first have to convert it into what's called conjunctive normal form, and then from the conjunctive normal form, you can convert it into a network. So that's a very interesting exercise. Okay. But the problem we had is that we normally were just given a bunch of data. We're not given a logical expression, and we want to have a method for learning the weights in this neural network based on that data. So this is where the field got stuck up until 1986. Now, what happened in 1986? Well, there was this revival of neural networks, and people started to use, so throughout the late 80s and 90s, the typical, people use a variety of different things, but the most typical architecture was what's called a two-layer neural network. So you would have a bunch of inputs, and then you would have a hidden layer. So you'd have these, each node in the hidden layer would be computed from a linear combination of the weight multiplied by the corresponding input. And there'd be biases as well, which aren't shown in this picture. And then you'd have a transfer function, which, and then these hidden node activations would go into the output node. So in other words, exactly the same as what's drawn here, but the number of hidden nodes can vary. Well, the number of inputs is determined by the problem, and then you have very few choices really. For the architecture, you just kind of choose the number of hidden nodes. Right? So this was the favored architecture. Okay, so we want to be able to train it on non-linearly separable functions. So this is the XOR data just written down in a table. For this task, we don't have a training and a test set. We really just we're not concerned about overfitting. We're just concerned about learning the data, and it can be learned with a two-layer network. So you can design it by hand and come up with weights like this. But what we're interested in is we determine this architecture, and then we want a procedure that will automatically find the weights for us. So how do we do that? Well, let's start by writing this network down as we assign a variable to each weight and each activation, and then we write some mathematical equations for computing the network. So we were given these inputs x1 and x2. u1 is equal to b1 plus w11 x1 plus w12 x2, and then a similar expression for u2. So this is the linear combination, and then it gets put through the activation function. So y1 is some function g of u1, and y2 is g of u2. Then we do another linear combination here with its own bias, and we put it through another activation function, and we get the output. So this is simply writing down the neural network in mathematical equations. And so let's just remind ourselves, we don't have any control over x1 and x2, but what we are able to choose is these weights in the network. And for this small network, we have 9 different weights, right? So these are called parameters or weights, and we want to find values for them such that it will correctly classify all of these training items. So we can view this as cost minimization. So we define an error function or a loss function. The textbook, the modern day use, or at least the textbook tends to use the word loss function, so I'll try to stick with the terminology in the textbook, but it used to sometimes also be called an error function or a cost function, E. And the main one we choose is the most basic loss function is 1/2 of the sum over all training items of the actual output of the network minus the target value of the network squared. So it's the sum of the squares of the differences between the actual output and the target output. We'll talk a lot. I'll come back to explain where this actually comes from. The 1/2 is just there as a mathematical convenience because when we differentiate it, the 2 will cancel the 1/2. And the key idea here, well, there's 2 key ideas here. So the first idea is that we can view this as a kind of error landscape. So we've got this state space which consists of our weights. So there's this x-axis here is this kind of 9-dimensional space with these 9 different weights, and then the height is the cost. So if I specify any particular set of weights, you can you can assign those weights to the network. You can feed in all the training items, calculate the error for each one, and add them all up. So you get this kind of you get this function from these 9 weights to a error function, and we think of this as a kind of landscape, and we want to reduce, we want to get to the lowest, we want to find the point where the error function is the lowest. So ideally we want to get to this point here, and so the idea here is a kind of local search. So I start from some random values, and then I think about how I can make a small change to those values, and then I kind of repeat the process, and hopefully by making a number of small steps, I will get to the global minimum. Now, the problem with this, right, so why wasn't this done in the 1960s? Well, the problem is this multi-layer perceptron, originally people were using this step function at the hidden nodes. So at the hidden nodes, they'd have that linear combination, and then they would convert it to either 0 or 1. And the problem with that is that this is sort of an important point. So, with the step function, if u1 is negative, then y1 becomes 0, and if u1 is positive, y1 becomes 1. So if you change you change these weights in such a way that this still remains negative, that will still be 1, and it won't make a difference to the error. The error will only change when you kind of cross this threshold, you somehow cross this boundary, and suddenly this becomes positive, then this will change to 1. So actually, with that step function, the error landscape looks more like this part of the error landscape is what the thing typically looks like. There's like these flat regions, and then you get to a certain point and you suddenly jump to something else, right? And so if you're sort of making small steps on this landscape, you don't have any way of knowing whether you're improving or not. When you're in this flat region, you don't know whether you're improving or not. You know, you may make a small change to the weights and the error doesn't change, so you don't know whether you went in the right direction or the wrong direction. So the second key idea is to replace that discontinuous step function with a smooth function, right? So originally what they had was this. Well, it's drawn a little bit off, but it should step up at 0, or sometimes from -1 to +1. So instead we draw a function which looks similar to this but is smooth. And so the ones we typically choose are the following. So this one is called the logistic this function here is called the logistic sigmoid. G of s is 1 over 1 plus e to the minus s. And it has a symmetry. It's rotationally symmetric about this point here, 0 and 1/2. It's not obvious from the formula that it's got a symmetry, but it does have a symmetry. And then if for some reason you prefer to have things go between -1 and 1 instead of 0 and 1, then we use this function here, which is called tan h, or hyperbolic tangent. And if you rearrange this equation, you can actually write it in this form here, and this makes it obvious that these two curves actually have the same shape. It's just that it's been shifted down, stretched in one direction and squashed in the other, right? So it's been shifted and rescaled, but it's the same underlying shape. So if you replace the hidden node, if you replace the activation functions, if you replace these step functions with these smooth alternatives, then the landscape, instead of having these flat regions, it becomes smooth. And that's critical, right? If it's smooth, then we can make a small change and we can tell whether we're going in the good direction or a bad direction. And this is done by a method that's known as gradient descent. So the key point here is, and this is why this relies a little bit on multivariable calculus, but what we really want to do, so I said, you know, you can make a step, I mean, it's possible to just make a random step and see whether you went up or down. That's called hill climbing. But in fact, we can do something a bit more intelligent than that. If we can calculate the derivatives of the error function, then we can figure out, well, what's the direction? You know, I've got 9 different directions. I've got a 9-dimensional space here. I want to know which direction I should go in order to go downhill as fast as possible. That's called the gradient. And the way you do that is you calculate the partial derivative of the error function with respect to each weight. So that's the partial derivative keeping all the other weights constant. And you do this for each weight, and then what you do is you say, okay, I want the error to decrease, so I'm going to subtract from each weight the partial derivative with respect to that weight multiplied by a small number called the learning rate. Now we saw this eta, we saw the learning rate in the perceptron learning algorithm. In the perceptron learning algorithm, the value of the learning rate doesn't matter too much, but here it does matter. You have to choose the right kind of learning rate, and often we choose 0.01 or 0.001 depending on the situation, right? You have to choose this learning rate eta that tells you this, that determines the size of the step that you take. And so this, in terms of vectors, if you think about the vector that's composed of all of these partial derivatives, as I said, that tells you the direction to go in, which will reduce the error as quickly as possible. So again, like what you're doing here is what you're saying is, okay, I've got certain values for all these weights. I'm going to keep all these other weights fixed, but just change this one. Then what would happen to the error function? Would it change by a large amount? Would it change by a small amount? And so it's really measuring how sensitive the error is to that particular weight. And the more sensitive it is, the bigger change. So if increasing this weight, and again the sign is sort of this, so it's related to the perceptron algorithm, but not quite the same. But this, the sign, obviously, if increasing this weight increases the error, then we want to decrease this so that it'll decrease the error, and vice versa. If by increasing this weight we decrease the error, then that's what we want to do. And again, you've got to go back and revise your high school or second year calculus. We use the chain rule to calculate these derivatives. So the chain rule says that if y is a function of u and u is a function of x, then dy by dx is dy by du times du by dx. And if y depends on u and v both depend on x, then you would say that dy by dx is dy by du, du by dx plus dy by dv, dv by dx, right? So we need the chain rule, and then the other thing, of course, we need to be able to do is differentiate the transfer function. So the derivative of the sigma, if we looked at the sigmoid and the tan h, you can sit down and calculate these partial derivatives yourself. The derivative of tan h is sec h squared, and the derivative of this is minus e to the minus s over 1 plus e to the minus s squared. So you actually, minus e to the minus over 1 plus e to the minus s. In the old days, interestingly, you can write the derivative in terms of the original function. In the 90s, when computers were slow, this kind of thing made a difference. Today, with modern computers, you can compute an exponential in one clock cycle, so that doesn't really make a difference, but these formulas are sort of interesting theoretically in any case. So using these two components, it's possible, it's tedious but possible to calculate the derivative of the error function with respect to every one of those weights, because the derivative of E, E is a half of z minus t squared, so the derivative dE by dz is z minus t. dz by ds is the derivative of the transfer function. And then if the derivative of a linear function is just a linear coefficient, and so on. So this is quite tedious. Now this is in the old, like I say, the people who were doing this in the old days, well, if it was a simple model like this, you could just do it with matrix multiplications in MATLAB or something. It was pretty simple. But if you had an exotic, if you started introducing exotic architectures or exotic transfer functions, people had to do all this by hand. They had to sit and write out all the equations and differentiate them. I think I went through this process once when I was trying to do trajectory planning for a wheeled robot, and you've got to look at all the kinematic equations and everything like this, and then it's very difficult to debug it, and there's really a big headache. the good news is that now with PyTorch we have AutoGrad. So the software will actually differentiate the functions for you. If you specify the functions in the model, the Python modules will calculate these derivatives for you. So it saves you a lot of this tediousness. Now, just a couple more points. Why is it called backpropagation? Well, if you actually sort of sit down and try to write the code for this, what happens is you start with the output, you calculate the derivative with respect to these weights, and then you calculate the differentials here, and then you use these differentials to calculate the gradient with respect to these weights. So you see these differentials get used multiple times because the differential here will, because of the chain rule, the differential here is used to calculate the derivative with respect to this, you know, the derivative with... if there's 10 inputs, this differential gets used 10 times, right? So you save this in an array and then you reuse it. You don't recalculate it. So the term backpropagation, I think the paper was originally called calculating gradients by backpropagating differentials or something like that. So backpropagation is really just an efficient way of calculating these partial derivatives. The general learning algorithm is called gradient descent, and gradient descent actually was already being used for other things in the 1960s. Mathematicians and engineers and optimization people knew about gradient descent in the 60s. It's just that somehow they didn't talk to the neural network people, and the neural network people didn't think about the continuous activation function until later. And if you read Schmidhuber's history of deep learning, he goes into all these issues. Okay, so gradient descent. The other thing I should mention is that theoretically, because this is a local search, it is possible that you might get into a local minimum rather than the global minimum. And there's a lot of sort of debate about this. Some people say this is well, for some problems it is an issue, but for many practical problems it turns out that especially with very large dimensions, it often turns out that either you're unlikely to get stuck in a local minimum, or the local minimum is sufficiently good that it does a good job. Yeah, so there are ways of trying to escape from local minima, but often we just don't worry about those things and just use the local search and accept whatever the outcome is. Yeah, and usually it's in practical terms it's quite good. So I might just make one more comment here before we get... sorry. Just a couple more slides and then we'll take a break. This is a list of applications, the kind of applications that would often these two-layer neural networks were used for. I'm not going to go in detail into any of these because we really want to focus more on the modern applications of images and language and so on, but this just gives you an idea. This is just one example of a kind of application people looked at. So in this case, this is a database of medical tests that were done on a bunch of people on an Indian reservation, and some of them developed diabetes and some of them didn't. And so the task here is to, based on these measurements, try to predict whether the person will develop diabetes or not in the next 5 years. Right, so we've got 8 inputs here, and then we've got, it's a classification task, and this shows you the kind of heterogeneous data that people were dealing with, or still sometimes deal with. You know, the number of times the person was pregnant, if they're female, concentrations of various things in their blood, their weight divided by their height, their age, and so on. And, you know, this shows the kind of mean and standard deviation of all of these things. And this is the last slide before the break. So I just want to give you a flavour of the kind of issues that arise in training such a network, where these issues are still relevant today with images and so on. So the first thing is that we often rescale the inputs to be in the range of 0 to 1 or -1 to 1. So the reason for this is, if you look at that backpropagation algorithm, it's the weights in the lowest layer get multiplied by the input. The weights in the input to hidden layer get multiplied by the size of the input. So if you just feed in the raw data in this format, you notice like this one varies from 120 to 32. So there's a very, sorry, this one varies the most. The standard deviation is 115, whereas for this thing here, the standard deviation is only 0.3. So the network, because of the backpropagation, the network might give undue emphasis to this input as opposed to that input. It might say, well, because this input is varying a lot, it must be really important, so I'm going to increase the size of that weight. But this is quite arbitrary. I mean, we've measured this in micro units per milliliter. I mean, we could have measured it in micro units per liter, or you know, some other scale. And then if we measure it in different units, instead of 115, this might be something else. So this is really quite arbitrary. So in order to get rid of that bias, we often, as part of the pre-processing, we just scale all of these inputs to a fixed mean, you know, maybe a mean of 0 and a standard deviation of 1. So then the network will then tend to treat all of the inputs with equal importance. Now, for some of these data sets, there are missing values. Maybe someone a particular test wasn't done on a particular person, or the result got lost or corrupted or whatever. You have to have a way of dealing with that. So what we often do is just replace it with the mean value for that attribute. The weights have to be initialized to small random values. You can't start with all the weights being 0 because of the backpropagation. If all the weights are if the input to hidden weights are 0, the hidden to output weights can be 0. But if the input to hidden weights was 0, then, well, so let me. Right, with the backpropagation. So if these weights were all 0, then what would happen is that because these weights are all zeros, no matter what the inputs are, these activations would be, you get the same output every time, and then when you backpropagate, this would be 0, and so the backpropagation wouldn't get started. So you have to start with some random values, and the values also have to be different. So if I were to choose certain random values for these, if I were to choose certain random values for the weights coming into this unit, and then if I happen to choose exactly the same random values coming into this unit, then what would happen is that these two units would produce, for every because the weights are the same, these two hidden units would produce the same value for the same hidden unit. And then when we do the backpropagation, both sets of weights would be updated in exactly the same way. So if those weights start out identical, they would always stay identical. So you have to have different weights for each hidden unit so that they can kind of specialize in different things or learn different features. The learning rate you have to adjust. And then the momentum, which we'll talk about afterwards. So what happens if you choose the wrong learning rate? Well, typically what happens is this. If they choose a very small learning rate, the learning will be successful but will be very slow. If I choose a learning rate that's too large, the learning will become unstable. So this, if the learning rate is correct, then you'll move from here to here to here and just sort of move down until you get to here, and then you'll stop. If the learning rate was very big, it is a little bit bigger, then you may oscillate here from here to here to here and then back and forth, but you may still end up at the minimum. If the learning rate's very big, you start here and then you kind of go back, you'll oscillate outwards instead of inwards, and the weights will end up like infinite, right? So this is typically people run your experiment and you print out the value of the error function at each stage, and you try one learning rate and you see, okay, the error is going down but slowly, so I'll make it a little bit bigger, and then if you make it too big, you'll see it like jumping around. So there's a little bit of fiddling around to get the right learning rate. And just one last thing, online batch, mini batch, and experienced replay. Okay, so if you look at technically, the error function is defined to be the sum of this difference squared over all of the training items. So to apply this gradient descent in a very pure way, we would compute this for every item and we would add them all up, and then so we would fix the weights. Using those weights, we compute the error for every item. We add them all up. We compute and then we add up all the differentials, and then we change the weights. And then using the new set of weights, we go to every item. So this is called batch learning. In batch learning, we go through all of the training items before we make any change to the weights. We go through all the training items and then we make one change to the weights. Then we go through all the training items again and make another change to the weights. But that's a very slow process. So a more efficient thing, people say, well, I don't want to wait till I've gone through all of the training items. I'm just going to present one training item, and for that one training item, I'm going to calculate the derivatives based on its contribution to the cost function, and then I'm going to change the weights based on that, and then I'll present the next item, and I'll do the same thing. So for the first training item, you're not looking at the whole error function, but just looking at z1 minus t1 squared. For the second item, you look at z2 minus t2 squared, and this is called online learning, or is sometimes called stochastic gradient descent. And the reason it's stochastic is because you're making changes that are not the true gradient, but are kind of have some noise added. So theoretically, you're going in all these different directions, but theoretically, when you've gone through all the training data, all of those vectors should add up to the true gradient. But because the weights are slightly different each time, it sort of adds a little bit of noise in there, right? So sometimes the purists use the term stochastic gradient descent to describe this. So again, like in the old days, there was just this simple distinction: either you did batch learning or you did online learning. But then what happened when they started introducing all these GPUs? People say, well, we can process a lot of items in parallel, so it would be very wasteful for just do one item at a time. So then we get what's called mini batch learning. So mini batch learning means, okay, I've got 1 million training items. My architecture allows me to process 500 simultaneously, so I won't do the whole million, but I won't do one item. I'll do 500 items at a time. So that's called mini batch learning. And I just threw in experience replay here because it's related. So when we get to reinforcement learning, there are some situations where your hardware allows you to process things in mini batches, but you're only generating one item at a time. So let's say you're playing a video game and you're creating training items as you play. So if you created one training item and then trained the network and so on, that would be very slow. So what sometimes happens is you have two processes running simultaneously. So one agent is playing the game and creating training items, and they're being stored somewhere in memory, and then a separate process is grouping those things into mini batches and training the mini batches in order to take advantage of the parallelism. So that's called experience replay. Yeah. Okay, any questions about this? Good. Okay, let's take a 10-minute break and then we'll come back and talk about probability. Hey.
G'day. With the assignments, how much horsepower are we going to need on our computers?
You shouldn't need too much. And I mean, most people don't have a GPU. Most people either don't have a GPU or can't get anything to run on the GPU. It'll be something that you can run in a reasonable time on a CPU.
Right.
It's not going to be.
I
know. We look at. Oh yeah. I mean, some people use Google Colabs and this kind of thing. Yeah, we were looking at Stanford as a course on deep reinforcement learning. We were looking on their webpage, like they're saying, for one of their assignments, they were saying you need 20 hours of training. So,
what?
So we'll try to avoid that situation.
I just don't run overnight. Okay. Right. I'm relieved. Thank you.
I didn't quite catch the part where you said hidden layers, the initialization should be of different values, the weights. Otherwise, everything would end up having no change at all.
Yeah, if the weights for this hidden unit were the same as the weights for that hidden unit, if they're the same at the beginning, they would stay the same forever.
Why? I didn't get why, sir.
Well, because the gradient. Oh, sorry. Not only Sorry. Yeah, I should clarify. If the weights if the weights both into and out of this hidden unit were the same as the weights both into and out of that hidden unit.
Because so what equation do you check for that in this? Like, how can I understand that?
Yeah, because this dy Okay, so let's suppose V1 is equal to V2, and W1 1 is equal to W12, and W21 is equal to W22, and V1 is equal to V2. Well, in that case, these two things would be the same.
Delta 1
Delta 1 and
and
delta 2. And then, well, Y1 and Y2 would be the same because of these weights being the same. And U1 would be equal to U2. So dE by dV1 would be equal to dE by dV2. So you would make the same change to both sets of weights.
which could be considered as perfectly normal, no?
No, because if two hidden units are computing the same function, then it's a waste. There's no point in having both of them. Hey, how's it going?
Can you let me info your process? Because as a master of research student, I cannot use the final W to process.
Did you send me an email? Or
I have sent you an email.
okay. Let me take down your name and normally we don't. They don't do this anymore because they don't have enough resources. For that reason, it wouldn't be hard to do. Oh, you can't enroll this in my unit.
No, I have to get your permission. And Sarah out here.
What was your student number?
My ID. Oh, thank you. Okay. Thank you so much.
So the bright propagation that we calculate the gradient according to each this neuron, and we got the sum. So we got gradient for this.
It's back. You start from the top and work backwards. So you start with this, and then you calculate the differential for each of these neurons, and then from there you calculate.
Yeah. So once we got the derivative for this neuron, then we use the gradient descent to decide which way we choose to get the minimum.
That's right.
For the weight calculation, so I think first the output of the neuron is this the weight output?
No, that's the output value.
So it's the output given by the output layer.
That's right, exactly.
Which values for each neuron?
Yes.
Then we use a different input to get
No, you put in one set of inputs and calculate all of these values. So there's a forward pass and then a backward pass. So the forward pass, you start with the inputs, get the inputs, and then you get the output. Backward pass, you start with the output, you get the differentials here, and then
what's the all input at stake, right? So this one input to this, so how do we get the different values?
because if the weights are different, then for the same input you'll get different values here.
So the different neurons have different the weight activating method.
That's right. Different values for the weights.
And so the point activation function. So the same one I learned before. So I remember this is one drawback disadvantage for the sigmoid. So it's not zero center. So what will cost the weight? Did you say it will cost the weight or negative or positive?
Yeah, so it's often, for that reason, it's usually better to use 10H for the hidden nodes. For the output nodes, it depends, like, if you if you want the output to be 0 or 1, then it makes sense to use the sigmoid. So often we use tan H at the hidden nodes and then sigmoid at the outputs. I mean, you can use sigmoid at the hidden nodes and eventually it will work, but it will train faster and more smoothly than the tan H. Oh, this just means the weights. So in this case, you've got 9 different weights. We've just written 1 dimension here, but really it's 9 dimensional. So for every set of weights, you have a cost, you have a value for the cost.
So like for each weight is run like this, and value of the weight, and
This is meant to be one set of weights with another set of weights with another set of weights. But really, this isn't just one dimensional, it's like because there are 9 different weights you can adjust. So pick a particular value if you pick values for all the weights, then it gives you an error function. Yeah, and error value.
and
That's right.
so we adjust weight when
You adjust all of them by the same rule. So W, I should have put like W. For each weight W, you do this.
So like at first we have their values, and for each value we do this, and we compare the error to see if it's right.
This is guaranteed to reduce the error by a small amount. Because if the function is smooth, then by doing this, it guarantees you to go reduce the error as fast as possible. Like, which small step can I make that will reduce the error as much as possible? That's what this does. Yeah. That's right, exactly. Yeah, I should have made maybe 2 different pictures. So really, if you have the threshold, there wouldn't be any smooth parts at all. It would really be kind of, the whole thing would be jagged.
So like after we implement this,
Yeah.
it will become like this part.
Exactly.
And if we don't do that, it will just be.
That's right. Yeah.
Going from top and going back and just these 2 ways first,
Yes.
and then going back to just all these ways.
Exactly.
So it's we should use the adjusted value for later calculation or the after adjustment.
Normally we change all the weights at the same time. So we calculate we calculate all the differentials and then we change all the weights.
We want the change of V1 and V2 both effect W's.
That's right. That's right. You calculate these differentials using the current V1 and V2. And then you calculate the differentials for these weights are calculated using the current values of these weights. And then you update everything at once. So you put the same value on the
That's right. So I have to restart this.
That's right. Yeah, incremental mode is also called online. The same. That's the same as online learning. can still use, well, with one layer network you can use the perceptron rule, but people often do use backpropagation with one layer network. That's right. So if the data is not linearly separable, the perceptron rule might become confused, but the backpropagation will give a sensible answer. That's right. Good. Okay, there's just two other things I wanted to say before we move on to the next set of slides. The first thing I wanted to do is just to come back to what I was saying at the end of last week's lecture. So if you remember, I was talking about this as a credit assignment problem. I was saying the reason we couldn't learn this as a multi-layer perceptron with the step function was because if the answer was wrong, you didn't know whose fault it was. And this is one way to view this gradient descent is that it does the credit assignment. So if the partial derivative with respect to this weight is large, that means that tells you that you should be changing this weight as opposed to some other weight. You know, so basically, the differentials are actually giving you this information for some inputs. You know, for one input, it may be that you get the wrong answer, but the differentials tell you that actually this was the guy who needs to be changed and not that guy because his differential is bigger. Or it may turn out that this needs to be changed. You know, if the derivative with respect to these weights is large but these ones is small, then that means these ones are correct but this one is wrong. So it's kind of clever because at least in this particular situation, it solves this credit assignment problem. There was one other point I was going to make. This error function here, you'll notice that, so where was it? Here. In a minute we're going to talk about a different error function which is called cross entropy. But if we use this sum squared error, you'll notice something interesting. If the thing is correctly classified, then the gradient will be very small because you don't need to make a change. If the gradient is in the middle here, if the classification is in the middle here, close to the boundary, then you'll have a big change. But if the thing is sort of very far in the wrong direction, then the gradient becomes small again. And that actually kind of fits in to some extent with this picture. So if you had for example, let's suppose I had an x that was all the way over here. Right, so what this gradient descent is doing is these ones here, which are easily classified correctly, the gradient will be very small and they won't have much effect on the boundary. The same thing for these. It tends to be the ones on the boundary that have the biggest effect because that's where the gradient of the transfer function is steepest. And then if for some bizarre reason you had an x that was all the way over here, the gradient would actually become small again. So if you think about an x here, we'll have a small gradient. An x here will have a big gradient. If the x came over here, the gradient would become small again because we've gone to the other side of that sigmoid function. So what the network would, what that really means is that if the x is over here, the network is going to effectively be treating that as an outlier. It's so far away that it says, well, I'm not even going to bother to I'm not even going to bother to try to train on that because it's too far away from the boundary. Now, one of the things we're going to talk about next is an alternative cost function called cross entropy. And cross entropy doesn't have that property. So with the cross entropy, the cross entropy function puts heavy emphasis on things that are very badly misclassified. So if the x is over here, the cross entropy will make a big effort to desperately try to classify that correctly. Okay, so anyway, we'll get to that in a minute. Okay, so now I'm going to talk about some variations on back propagation, but start with some probability. Now, I mentioned that we kind of expect you really to know probability beforehand, but I am going to just review the things that we need for the course. And it's also in the textbook. So probability, if you go back, the origins of probability in the 16th century were often to do with gambling and focused on discrete probabilities. So we toss a coin, there are two possible outcomes that are equally likely. We roll a die, there's 6 possible outcomes that are equally likely. Right? We have a dice have 6 sides. So the outcome is either 1, 2, 3, 4, 5, or 6, and all of them have a probability of 1/6. And in general, if you've got discrete outcomes, all the probabilities have to be between 0 and 1, and the sum of all the probabilities has to be, if they're disjoint events, then the sum of all of them has to be 1. So that's like a atomic event, and then we can put together atomic events to make compound events or random functions of individual outcomes. So the probability of the dice being rolled and having if the probability of the outcome being less than 5, we can ask what's the probability that the thing rolled on the die is going to be less than 5. Well, that's the outcomes 1, 2, 3, and 4. So we add them all up. 4 times 1/6 is 2/3. So the probability is 2/3 that the outcome is going to be less than 5. This is, in a way, just sort of fancy notation, but we can define this as a kind of a function on these atomic outcomes. It could be a real valued function, or it could be a Boolean valued function. So in this case, we assign either true or false to each outcome, and then we have what's called a random variable, and then we can talk about the distribution of that random variable. And so in this case, the probability that the die being rolled is odd is probability of 1 plus probability of 3 plus probability of 5, which is 1/2. So that's discrete variables. Now in this course, we're going to also be needing continuous random variables. So with a continuous random variable, what we're really talking about is a probability density. So you draw a function which is positive, it's non-negative, right? It has to be either 0 or greater than 0, and the total integral under that curve has to be 1. So this is an example here. Let's say that this, so if you have a uniformly distributed random variable, let's say it's uniformly distributed between 18 and 26. Well, you have to make the curve, you have to make the thing have area 1, so the height is 0.125, so that when you integrate it, when you multiply two things together, you get 1. And of course, the value can be bigger than 1. The density can be bigger than 1. The integral can't be bigger than 1, but the density can be bigger than 1. If you had a uniform variable between 0 and a half, then the density function would be 2, but the integral would still be 1. So what this really means, it doesn't make sense to ask, well, what's the probability that x is exactly 20.5, because it's, if it's a continuous, if it's really a continuous variable, then the probability would be 0 for any particular value. So what we really mean is that we're picking a very small neighborhood with a width of delta x, and so we're actually asking, well, what's the probability that the value is between 20.5 and 20.5 plus dx, and we calculate that probability and divide by dx, and the answer is 0.125. So that's the real interpretation, right? So the probability of the value lying in this rectangle, in this interval, is the width of the interval multiplied by 0.125. So this is a continuous distribution that often is used in practice. The other one that's most commonly used is the Gaussian distribution. So this is, or sometimes called the normal distribution. So it has a mean and a standard deviation. This picture has a mean of 0, but it could have any other mean. And the formula is the following: e to the minus x minus mu squared over 2 sigma squared. And then we have to multiply by a normalizing constant, which turns out to be 1 over square root 2 pi times sigma. So it's very important to remember this formula. And it's got this very distinctive shape. And you come across this in statistics all the time because of the law of large numbers. So if I, like I said, if I were to toss a coin 1,000 times and count how many times it comes up heads, on average we would expect it to come up heads 500 times. But if you repeated this experiment multiple times, very tedious, you ask 100 different people each to toss a coin 1,000 times, you would actually, and report to you the total number of heads, it would fall on this distribution. And we'll see an example of this later in the course, how to calculate that standard deviation. So if you add up a large number of independent variables, it always has this kind of distribution. Now we also need to look at the interaction between probability and logic. So logically related events must have related probabilities. So the probability of A or B occurring is the probability of A plus the probability of B minus the probability of A and B. So you see this is a Venn diagram, right? The white region is, the area of the white region is this circle plus this circle minus this little bit in the middle, which has been counted twice. And this leads to conditional probability. So if so long as the probability of B is not 0, then the conditional probability of A given B is written like this, and it's equal to the probability of A and B divided by the probability of B. So what this is saying is the probability of A happening given that you know B has happened. So if we know that B has happened before I tell you that B has happened, then everything in the square is possible. But once I tell you that B has happened, you know that you're restricted to this circle, and then this is saying given that you're restricted to the circle, what's the probability of A? So it's actually the area of this little sliver here divided by the area of the circle. So this is the probability of A given B is the probability of A and B divided by the probability of B. Right? Now, when I was preparing these lectures, I kind of noticed something interesting. When you see people draw these Venn diagrams, they almost always draw the two circles the same size, but in a way that actually just totally misses the most important point, because in general, these circles are different sizes, and so the probability of A given B is different from the probability of B given A. Right? So the probability of A given B is this intersection divided by this big circle, but the probability, so it's very small in fact, but the probability of B given A is the same sliver, but it's divided by this smaller circle, so that you get a much larger number, right? And this is where we have Bayes' rule, which actually is the relativity between these two conditional probabilities. So the probability of A given B, so let's have a look at this individually. So the probability of A and B is the probability of A given B times the probability of B. So this probability is here. You start with the probability of B, and then you multiply by this divided by probability of B, right? But you could get it the other way. You could say, well, this is the probability of B given A times the probability of A. And then if you juggle this around, you say the probability of A given B is the probability of B given A times the probability of A divided by the probability of B. That's a mouthful. Now, we usually, the normal context in which this arises is where you have a cause and then you have an effect. So A is the cause and B is the effect. And so we've observed an effect and we want to go back and say what's the probability of the cause. So often we know the probability of the cause producing the effect, but we want to figure it out this way around. Okay, so here's a couple of examples. As some of you may have seen this one before. This is about medical diagnosis. Let's suppose, right, so this is a situation where those two circles are very different sizes. So let's suppose we have a test for a certain type of cancer which occurs in 1% of patients. The test has I've split it up as sensitivity and specificity, so it's quite an accurate test. The accuracy is 97 or 98%. And then the question is, a patient comes in and the test is positive, so what's the probability that they have the cancer? And so I always forget these words myself, but sensitivity means if a person has cancer, what's the probability of the result coming back positive? So that's the likelihood of a true positive, and the specificity is the likelihood of a true negative. So if the person doesn't have cancer, what's the probability of it coming back as a negative result? Often we assume that these two things are the same, but in general they could be a little bit different. And so how do we answer this question? Well, we could draw it as a Venn diagram, or we can draw it as a kind of, with arrows showing the sequence of events. So the person either has, before they've taken the test, they either have cancer or they don't. And so before they've taken the test, if someone just randomly walks in and hasn't had the test yet, and we want to ask what's the probability that they have the cancer, our best guess is 99% they don't have it and 1% they do have it. That's called the prior distribution, because that's called the prior probability because that's our estimate of the probability before we do the test. Now, if they do have the cancer, then the probability of the test being positive is 0.98 and negative is 0.02, and if they don't have the cancer, it's 0.03 and 0.97. So then what we're asked here is, given that the test is positive, what's the probability that they have the cancer? So if we told that the test is positive, we're restricted to this line and this line. So the two negative cases have been excluded, and we've just got this and this. And so we can figure this out by multiplying these probabilities. So when I multiply these 0.99 by 0.03, I get 0.02. I'm just going to round it off. It's so close to 0.03, I'm just going to round it off to 0.03. And here, 0.01 multiplied by 0.98 is basically 0.01. And so the probability that they have the cancer is this divided by this plus this, which is 1/4. Right? So some people have, the average person in this, I'm sure you people are all very sophisticated, but the average person in the street really struggles to understand probability very well. People sort of think, because the test is 98% accurate, people think, well, if you test positive, it must be very likely that you have the cancer. But because the cancer is so rare, it's actually somewhat more likely that the test was wrong. The likelihood of the test being wrong is higher than the likelihood of you having the cancer, right? So even though the test is 98% accurate, there's really only 1 chance in 4 that you really have the cancer. Okay, so this is a case where it's a Venn diagram with one bubble much bigger than the other. You can have a look through this yourself. This is very similar, but I just wanted to show you an example where it's not quite so unbalanced, but it makes a little bit of a difference. So you work for a lighting company which manufactures 60% of its bulbs in factory A and 40% in factory B. 1% of the bulbs from factory A are defective and 2% from factory B. And then we say, if a random light bulb is defective, what's the probability that it was manufactured in factory A? And again, we draw the same kind of diagram. So before you knew that it was defective, you would have said that if you just had a random light bulb and you don't know if it's defective or not, you'd say there's a 40% chance of it being from factory B. After you find out it's defective, you change your estimate. Beforehand you would have said there was a 60% chance of it being from factory A, but because the light bulbs from factory B are more likely to be defective, once you find out it's defective, you increase your estimate of it being from factory B and decrease your estimate of it being from factory A. So instead of 60%, you say it's 3/7, right? So it's not an enormous difference like in the cancer case, but it's a significant difference. It's gone down from 3/5 to 3/7, right? So, I mean, it was bigger than a half, and now it's less than a half. And sometimes these differences are important. Okay, so we're going to come... I'm trying to get through the probability first, and then afterwards how this relates to the backpropagation variance, right? So we're going to come back to this Bayes rule. Now, another important thing for the later part of the course is to understand a little bit about information theory, and in particular the entropy and the KL divergence. So if we have a discrete probability distribution, so again this goes like the example with the dice with 1/6, or here the probabilities, we have n possible outcomes and they could have different probabilities. The entropy is defined to be the sum of pi times minus log of pi. I'll show you a couple of examples of this. And then sometimes we have two distributions and we want to measure the distance. How different are these two distributions? How much is this distribution different from that one? And we often do that using what's called the Kullback-Leibler divergence, or the KL divergence, which is defined this way. This is like a distance, but it's not symmetric. So the KL divergence from P to P is always 0. But the KL divergence from P to Q is not necessarily the same as from Q to P. So we don't call it a distance because a distance has to be symmetric. But it behaves similarly to a distance. All right, so let's look at some examples of entropy, and the best way to understand this is in terms of information theory. So let's say this is the example of like a coin toss. If you toss a coin, there's two outcomes and they're equally likely, so 0.5 and 0.5. And the entropy of this is 1, because in information theory we always compute logs base 2. Log base 2 of a half is 1. No, log base 2 is half is minus 1, so this is why we take minus log base 2 is 1. And so you've got 0.5 times 1 plus 0.5 times 1, which is 1. And we call this 1 bit. So it's best to understand this as a coding theory. Let's suppose someone is sending you a message. You have to encode them. You and I have to communicate, and we send messages to each other, and the messages consist of strings of A's and B's, and A and B occur equally often, and we have to agree on a code. The most efficient code we can have is we just say that A is equal to 0 and we have to agree on a binary code. We can only send zeros and ones to each other. So the most efficient way to do it is to say that A equals 0 and B equals 1. Or A equals 1 and B equals 0. So you send me 00110 and I know that means AA, BBA. And we can write this as like a little Huffman tree. And you can see I'm assigning exactly 1 bit to each letter. So the entropy is the average number of bits you have to send for each letter. And here's a slightly more elaborate example. This time we have 3 letters A, B, and C, but they don't occur equally often. A occurs more often than the other two. So half the time, half of the letters are A. On average, half of the letters are A, and 1/4 are B, and 1/4 are C. So it's more efficient because A occurs more often, it's more efficient to have a shorter code for A. This is what you know, the principle of Morse code as well is like trying to have shorter codes for the commonly occurring letters. So one way to achieve the most efficient code here is to say, well, 0 is going to be A, 1, 0 is going to be B, and 1, 1 will be C. So if, as you're decoding the message, you see a 0, you know that's an A, and you know the next letter is about to start. If you see a 1, you have to read the next digit, and if it's 1, 1, then it's C, and if it's 1, 0, it's B, and then you know that the next digit is going to start. We assume that we assume the message is being sent without any errors. Of course, if you miss a digit, you would get confused, but we assume that you're receiving the message perfectly. So the average, when you send an A, half the time you're sending an A, which is costing you 1 bit, and the other half of the time you're sending a B or a C, which is costing you 2 bits. So on average, each letter on average is being encoded in 1.5 bits. And if you calculate the entropy, it's exactly 1.5. Right? Now, these are simple examples. In the more general case, so let's suppose that A, B, and C occurred equally likely. They all occurred with probability 1/3. We wouldn't be able to come up with a neat code like this. If we wanted to send the message efficiently, we would have to use what's called a block coding. So we block the, we block the message into several. Let's say we block the message into. If we send 2 letters at once, then we have 8 different 2 letters at once, we'd have 9 different possibilities. If we have 3 letters at once, we have 27 different possibilities. We have AAA, AAB, AC, etc. The 27 possibilities. Well, for each of those 27 possibilities, we could use 5 bits. Because 5 bits gives us 32 possibilities. We've got 27 out of 32. So if you block you can never come up with one code that'll achieve the entropy. But if you block the letters into large enough blocks, you can achieve a code which is very, very close to the entropy, right? So the entropy, in general, this entropy represents the most efficient code we could have if we send multiple letters at a time. Is there any questions about this? Now, what about KL divergence? Well, KL divergence also has an interpretation in terms of coding theory. What this is actually saying is I'm sending a code you and I you come up with a code and I come up with a code, and we're using the same letters, but you think that the distribution of letters is going to be given by P, and I think that you come up with a code and you think that the probability distribution of the letters is going to be Q, but after you've designed the code, it turns out that the true probability distribution of the letters is actually P. And so the KL divergence measures the wastage, how many extra bits you're going to have to send because you made up an inefficient code. You designed a code that was efficient based on the probabilities Q, but in reality you had to send a message based on P. You know, so let's say, I don't know, you based your probability you based your code on the occurrence of letters in English, but then it turns out you have to send actually messages in German. So if the distribution of letters is very different in the two languages, the difference between how many bits you're actually sending and how many bits you could have been sending if you had designed an efficient code. Yeah. So it's a little bit, but this is actually a nice interpretation, right? So that measures the distance between these two probability distributions. Now, when we move to continuous variables, we don't have quite the same neat interpretation, but the formulas become the same, just written as integrals instead of sums. So if you've got a continuous probability distribution P, the entropy is the integral over theta of p theta times minus log p theta d theta. In continuous variables, sometimes we use log base 2, sometimes log base e. It doesn't really matter as long as you're consistent. It just multiplies it by a constant. And we would have to interpret it by saying that I'm sending a message. Basically, you have to interpret it by saying, well, I'm choosing a point from this distribution and I'm sending the value of that point, but I'm only sending it to 3 decimal places, let's say. You know, and how many... So if I want to send it to 3 decimal places, how many bits would I need to create that kind of coding? Now, it turns out for a Gaussian distribution, the formula for the entropy is just the sum of the logs of... well, for one variable Gaussian distribution, the entropy is the log of the standard deviation. And if you've got a product of Gaussian distributions in multiple variables, then the entropy of the combined distribution would be the sum of those logs. And the formula for KL divergence is, again, it's the same but written as an integral. Okay, so we'll be using this later in the course. We'll be using the KL divergence when we get to variational autoencoders in the very end of the course. It's also used in some reinforcement learning algorithms, but we might not get into too many details about that, but it's important to understand this. So often in neural networks, often what happens is that we have a distribution P. Well, often what happens is we have a distribution P, and then we want to choose a distribution Q which is close to P. We want to kind of approximate a given distribution, and so we use the KL divergence actually as a loss function when we train our neural networks. And so you can do it either forward or reverse. So in some situations, we're given a distribution P, and then we want to find a Gaussian distribution Q, which minimizes the KL divergence from P to Q. And in other situations, we want to minimize the KL divergence the other way. Now, the forward KL divergence, this is used in situations. This is generally used in robotic situations where you're trying to track a target. There's a target that's moving around and you're trying to follow it so that you can shoot it, or you're trying to follow it so that you can dock with it. You know, like there's a space station and you're trying to dock with it, so you have to estimate its position. In that situation, or it's trying to shoot you and you're trying to keep track of where it is so that you can run away. Now, in that situation, we always minimize the forward KL divergence. So let's suppose that the blue distribution is the real, the blue is the real kind of best distribution we can guess for that object that's trying to shoot us. But we're using a Gaussian, it's bimodal here, but we're trying to approximate it with a Gaussian. This would be a very bad choice because the green distribution being here means we're very confident the thing is here. So we think it's safe to go over here, but the thing may actually be there, in which case it'll kill us, right? So a much safer option is this one, which kind of straddles those two possibilities, because if we use this distribution, we're aware of the fact that it could be here or here, and so we know that neither of these places is safe, so if we want to escape, we have to move somewhere else, right? So if we use the forward KL divergence, in this situation, the forward KL divergence is large. There's a very, very high penalty, but here is where it's minimized. Okay, so that's target tracking, but this is reverse KL divergence is relevant in a different situation. Let's suppose we want to learn how to play a video game, and this blue distribution perhaps, let's say the blue distribution is actually models the way humans are playing the game, let's say, and we want to model that, or well, and let's say that this is concentrated in places where you get humans who get a high score sometimes use this strategy and sometimes use this strategy. Well, our objective is just to find a strategy which achieves a high score. So it doesn't really matter whether we pick this or that peak, because we're going to get a high score in either case, right? So we're not necessarily trying to cover all the possibilities. We're just trying to find one way to achieve a high score. So, and in fact, if we try to straddle the two of them, this may be bad. It may be that this gets us a high score and that gets us a high score, which is why the humans are playing there. But if we go for this middle strategy, we might actually get a low score. So in that, in this sort of reinforcement learning situation, we often try to minimize the reverse KL divergence instead of the forward KL divergence. So like I say, this will become relevant later in the course, but I think it is good to introduce you to these ideas early. Does anyone have any questions about this? Good. Okay, so that's the probability. So now we move on to how this is relevant to backpropagation. And I'm going to discuss 3 different variations on backpropagation. So the first is called cross entropy. The second is weight decay. And the third is momentum. And we're going to use these ideas from probability to explain the motivation for these things. Okay, so let's start with cross entropy. Now, if the target, so sometimes we want to do function approximation. Sometimes with supervised learning we have an input and then we have an output, and the output might vary continuously. Now in that situation the sum squared error is a good choice. But in a lot of situations we're trying to do classification. We're just trying to say effectively we're just trying to output 0 or 1 because we're trying to say whether the person is likely to develop diabetes or whether it's a picture of a cat or a dog. You know, we're trying to put it in one category or another. And because the output should be 0 or 1, it's often better to use a different, instead of the squared error, it's often better to use this function here between t and z. So the loss function is minus t log z minus 1 minus t log 1 minus z. Now, I'm going to explain the mathematical motivation for this in a minute, but let's just think about this sort of from a practical point of view. So remember what I mentioned before, that with the sum squared error, if something's very badly misclassified, eventually it will be ignored by the network because of that sigmoid function becomes flat. Now, in this, if you use this function, if something becomes very badly misclassified, if the output is supposed to be 1, if t is equal to 1, but z is close to 0, you get this log of a number close to 0, and that actually kind of blows up to infinity. So the further the thing, no matter how badly misclassified it is, the network will never learn to ignore it. It'll always, it'll get, the more badly it's misclassified, the bigger the error, the bigger the loss function becomes. So this forces the network to put heavy emphasis on the things that are badly misclassified, which is often, if you're very confident, again, a lot of time it comes back to how much confidence you have in the data. If you think that some of your data might be mislabeled, you probably don't want to do this, but if you're very confident that the labels are accurate, this is often a good choice. It's also beneficial in situations where you have unbalanced data. So you're trying to do credit card fraud detection. You may have, let's say you have 100 examples where there was credit card fraud, but then you have 10,000 examples where there was no credit card fraud. There's a risk with any machine learning algorithm, because there's 100 negatives for every one positive. There's a risk with any machine learning algorithm that it may just classify everything as negative. Then it'll achieve 99% accuracy, but that's not really what you want. So this is good in that situation as well, because no matter how, even if the positive examples are very few in number, it forces the network to give them a lot of emphasis to them. Okay, so this is the kind of hand-wavy argument. Now let me show you the, it's also interesting, it simplifies the equations as well, because if you're using the sigmoid function, if you differentiate that function, you get this, and the denominator is actually the derivative of the sigmoid function. So these sort of cancel each other out. All right, now what's the mathematical motivation of this? Well, here we get to what's known as maximum likelihood estimation. So this is kind of general machine learning terminology. So we have a class of hypotheses. Now in our case, a hypothesis is a set of weights, set of values for the weights of, we have a neural network, and a set of weights for that network is called a hypothesis. And then we have this data that we've observed. So in our case, the data is these pairs of inputs and target outputs. And So what we want to do is maximize the probability of D given H. This is saying, well, what's the probability of certain data being observed given that hypothesis? So just before we get to neural networks, let's go back to linear regression, because this is where we can understand this a little bit better. Now, I hope. Right, so here the hypothesis is the line, and the data are these values. And you've got effectively this. So this value here is the input. This value here is the output, right? So in this case, it's just a very simple function. It's a linear function. But if this was a neural network, it would be determining this value z, and then this number here is the target output, and so this distance here is z minus t, and I'm sure most of you have seen this procedure, that when we try to find the line of best fit, we try to find the line that minimizes the sum of z minus t squared for all of these data points. So I think most of you are familiar with this procedure, but you probably never stopped to sit down and think about where it actually comes from. So now I'm going to tell you, well, why? So the first thing you've got to understand is why don't the points lie exactly on the line? Well, this one here, maybe it's because it's an outlier. We maybe could discard that. But these other points, it's because of measurement error, basically. So because of the calibration of the equipment, or the air resistance, or the friction, or all these tiny little factors adding up, creates this discrepancy where the measured value is slightly. We assume that this is the underlying physical process, and the reason that this is slightly different from this is because of these factors that all contribute randomness to these values. And if we assume that there's a large number of them, and they're all independent and they're just being added up, then it's kind of like tossing a coin 1,000 times. And so because of the law of large numbers, we assume that there's a Gaussian distribution here. So we don't expect to measure exactly this value, but we expect that the probability, we expect these points to follow a Gaussian probability distribution with this mean and some standard deviation. We don't know what sigma is, but we assume that this is the mean. Okay, so this is our underlying assumption. So if we just write out these equations, so as I said, the hypothesis here is really that function, that linear function, and the data are these target values that we've observed. So we assume that the probability, given a particular function, the probability of observing those target values is for each one is this Gaussian distribution, and so we multiply all these Gaussian distributions together, right? So that's the we want to maximize this probability. We want to choose the line which is most likely to produce the data that we've observed. So if we calculate the log of this probability, well, the log of a product becomes the sum of the logs. This constant factor out the front becomes this, adds this constant term, and this then log of e to the minus something is just the minus the something. Now remember, we're trying to choose, the only thing we can have any effect, the only thing we have any control over is f. So because we're trying to maximize this, we can ignore these terms here because they're just constants, so we can throw them away. So we're trying to maximize this. And this is just a constant as well, 1 over 2 sigma squared. And there's a minus sign. We're trying to maximize something with a minus sign, so if we take away the minus sign, we want to minimize it. So this probability will be maximized when we minimize the sum of the squares of these differences. So now you can, all these years you've been up late at night wondering where this formula came from. Now you can sleep soundly because you know its origin. Right? The interesting thing about this, we don't need to know sigma. There is a sigma there somewhere, but we don't actually need to know what it is. So this is the derivation of least squares. Right, so what's the derivation of cross entropy? Well, how do we interpret this? How do we interpret classification as a probability? So let's say you've got a neural network that's trying to tell you whether an image is of a cat or a dog. So let's say the cat is, an output of 1 means that it's a cat, and an output of 0 means that it's a dog. If the network outputs 0.8, what does that mean? Well, the only sensible way to interpret that is to say, well, that means it thinks there's an 80% probability of it being a cat, right? If the network outputs 1, that means it's certain to be a cat. If it outputs 0.5, that means it's equally likely to be a cat or a dog. If it outputs 0.8, that means there's an 80% chance that it's a cat and a 20% chance that it's a dog. So whatever the network outputs, we just interpret that as a probability, right? So on that basis, if this output of, so I'm using f of xi to be the output of the network. It's a number between 0 and 1. So that the probability that of the output being 1 is just f of whatever the output is, right? So if the output is 0.8, then the probability of the thing being 1 is 0.8. And if the probability of it being 0 is 1 minus 0.8, which is 0.2. So we put these two things together. This is actually, this formula is actually this formula actually does make sense when the TIs are not, even if the TIs were between 0 and 1, this formula actually does make sense. It's related to the KL divergence we talked about before, but we can just think of this as if TI is 1 or 0, you can just think of this as a fancy way of combining those other two equations, right? If TI is 0, then this term disappears, and I get 1 minus f of xi. If TI is 1, then this term disappears, and I get f of xi. So this, you can think of this as just a fancy way of writing that. And then if I calculate the log of this, I get TI times log of fxi plus 1 minus TI times log of 1 minus fxi, right? Which is the formula for cross entropy. Does that make sense? Yeah. Okay, so that's cross entropy. Now, the next The next variant we're going to talk about is weight decay. So sometimes we add something to the loss function to encourage the weights to stay small. So we may have our original error function, which is a sum of zi minus ti squared. But if I add, and this is sort of the beauty with this PyTorch, that you can just add extra terms to the loss function and it'll calculate all the derivatives and figure everything out for you. You can play around with it. So what we often do is we say, okay, I'm going to add the sum of the squares of the values of all the weights in the network. And I'm going to treat this as a loss function. So this is something that's supposed to be minimized. And I'm going to multiply it by lambda to measure how important this is. You know, lambda in this situation is typically maybe 0.0001 or something. So I'm mainly trying to minimize the squared error, but this gives the net this basically says I've got a slight preference for smaller weights. You know, if you can produce the same error with smaller weights, I'd prefer that rather than having larger weights. Is basically what's going on here. So, so again, I'm going to talk about this like in practical terms first, and then look at the mathematics. So, again, because of that sigmoid function at the hidden nodes, or the tan h, if the weights get to very large values, then it kind of pushes those hidden units to the extremities of the sigmoid, and it starts to look a bit like the the old-fashioned threshold function. And once that happens, sometimes it becomes hard for the network to continue learning. So by encouraging the weights to stay small, we kind of maintain the flexibility of the network. And this is particularly important in situations where the function you're trying to learn may be changing over time for some reason. So that's one motivation. Sometimes this is referred to as elastic weights. So the reason it's called elastic weights is because, again, if you take the derivative of w squared, you get w. So this is actually, if you studied spring, if you did in high school physics, maybe you studied these situations where you have a spring and you have a block on the end of the spring and you pull the spring out and there's a force pulling the block back which is proportional to the distance. And that's exactly what's going on here. Like, it's as if when the weight gets large, there's a force trying to pull the weight back to zero, and the size of the force is proportional to the size of the weight. Okay. Well, all right. So now let me tell you the mathematical derivation of this. This is where we go. We need the Bayes rule. So Bayes rule in this context, instead of A and B, we use D and H, right? So we have a hypothesis and then we have the data. So the hypothesis is the cause and the data is the effect. And so often we can calculate the probability of the data given the network. Often we can calculate the probability of D given H, but what we really want to know is probability of H given D, right? So we've observed certain data and we want to know what's the likelihood of a given set of weights based on that data, and so we use Bayes' theorem to calculate it. Okay. Now this may look a bit a bit crazy at first, but this is really just all that's going on here is you taking Gaussian distributions and taking the logs and so on, right? So this is saying, okay, so in our situation, we observe certain target values for a set of inputs, and we want to know what's the probability of a certain weight given those target values. And we want to find the set of weights which maximize this probability. So this is the probability of the target values given the weights multiplied by the probability of the weights divided by the probability of the target values. So previously we just maximized this. We maximized the likelihood of the target given the weights, but really it makes more sense to maximize this because we want to take account of the idea that some weights might be more likely than others. So we start with the assumption that small weights are more likely to occur than large weights. So we often assume a Gaussian distribution for the weights. This is our prior distribution before we've seen any data. So then this becomes this. So probability of t given w is this thing here that we maximized before. Probability of w is this Gaussian 1 over pt. Now remember, we're trying to maximize this. We don't have any control over t. We don't have any control over t. We've only got control over w, so we can ignore this term. We don't know what it is, but we can ignore it because it's a constant. So we just need to maximize this. Now again, we take the logs. The log of a product is the sum of the logs. So we get this term that we got before, and then we get this additional term here. And this exactly gives us this weight decay, right? So yeah, it's simply saying that we want to favor smaller weights rather than bigger weights. Now in practice, yeah, you got this value lambda, which in practice you have to fiddle around with. You just have to try one value and then try something else. There isn't like a methodical way of deciding what lambda should be. Okay, one more slide. But it'll take a little bit of time to explain this. So this is momentum. Now, I'm trying to I'll try to do this using the document camera for the benefit of the viewers at home. So the motivation here is as follows. Well, let's suppose that you have a... Oh, I can't really do this in front of the camera. Let's suppose you have a situation where the landscape is shaped like a kind of rain gutter. So there's a kind of, half a cylinder here. So then if it was a perfectly flat cylinder, then you used gradient descent, then you would just kind of rock back and forth, right? But now let's assume it's slightly tilted, right? So it's like this, but there's a little bit of a tilt here. So really what you want to do in order to decrease the loss function is to go down in this direction. But if you use like ordinary gradient descent, what would happen is you start here, the gradient takes you here, and then here, and then here. So you're sort of, you're expending most of your effort just kind of rocking back and forth and only making very slow progress in this direction. So this is the situation we should think of. So the way we deal with this is we maintain a running average of the gradient. So instead of just go back to these equations. So now, by the way, there's a couple of different formulations of this, but I've tried to use the one that's consistent with the textbook, and it's also what's on Wikipedia. So I maintain delta W. So delta W is actually a running average of the gradient. And so when I calculate my gradient, I say, okay, I'm just going to make a slight change to my, well, let me back up a bit. So one way to do this would be as follows. No, where was I? Oh, sorry. Yeah, I'm just going to, I have this parameter alpha called the momentum. Now, typically, let's say the momentum might be 0.9. So I had a previous estimate of what the gradient was. Now I've calculated the gradient of the next training example. I'm just going to make a slight change to my previous estimate. So I'm going to take 90% of my previous estimate and then add on the learning rate times the new gradient. So this, effectively, this averages the gradient over multiple training examples or multiple mini batches. It's sort of, it's kind of like, yeah, what I was going to say before is you could approach this by saying, well, I'll calculate 10 mini batches and I'll average the gradient over those 10 mini batches. But by making this as a running average, it's like, in principle, it's the same as kind of averaging over the previous 10 or 20 calculations, but I'm just sort of continuously update. I'm just keeping one value and sort of continuously updating it. I don't know if I explained that well. So I take 90% of the previous gradient and just add in the next value. And then I use that to update my weights. So the effect that this has, I don't have any mathematical justification for this, but just what happens is you calculate this gradient, and then this is the next gradient, but my delta W is going to be this kind of averaged with this. And then I'll average it with this and average it with this. And so this sort of, what will start to happen is these crosswise components cancel each other out, and the components that take you in that direction emphasize each other. So it'll sort of have this effect like this, where you end up going further in the correct direction. You know, in theory, it should the oscillation, the sideways oscillations should cancel each other out, and the speed with which you go in the correct direction should get multiplied by 1 over 1 minus alpha. So if alpha is 0.9, ideally you should be ended up the correct direction should get multiplied. You should go 10 times faster in the correct direction. That's in the kind of idealized situation. In practice, I don't know if it always works that well, but it tends to produce a pretty good result. Yeah. So this, it dampens out these oscillations. Another effect is if there are little bumps in the fitness landscape, this often helps you to kind of ride over those bumps. Okay, so that's momentum. So often this is what happens. When you train a neural network model, you choose a learning rate, you choose a momentum, and you choose weight decay. Okay, let me just make a couple more remarks before we go. I didn't prepare slides for this, but let me just say quickly, there are other variations that we're not going to talk about. So one set of variations are quadratic algorithms. So there's this thing called conjugate gradients. Now, conjugate gradients works by calculating second derivatives. So you calculate not only the derivative with respect to each weight, but you calculate the second derivative with respect to each pair of weights. Now, this is a method that people sometimes used in the old days, but people generally don't use that anymore because the number of weights is too big. So if you had, in the days when people had 100 weights in their network, you had to calculate 10,000 second derivatives, which was fine. In deep learning, we often have 1 million weights in the network. So or even if you have 100,000 weights in the network, there's no way you could possibly calculate all those second derivatives. So there's quadratic methods like conjugate gradients we generally don't use anymore. The other thing I was going to say, there are other variants of this. One of them is called ADAM, which is adaptive momentum. And I don't want to go through the equations of ADAM. I just want to say the idea is that it's supposed to do the same kind of thing as momentum, but calculate the momentum automatically and do it independently for each weight. And you don't really have to understand how ADAM works, but when you get to PyTorch, there's an option. You can choose SGD, which stands for stochastic gradient descent, or you can choose ADAM. And somehow, in a lot of cases, ADAM does give a better result. Yeah, so I don't fully understand, even myself, I don't fully understand how it works, but often it's a good thing to try. Yeah, and there's been a few of these things experimented with over the years: RMS prop, ADA bound. There's a bunch of them, but ADAM seems to be the one that people are happy with, that works most of the time. Good. Okay, so there's been quite a lot of mathematics today, but I think it's been useful, and I'll see you next week. Yeah.
Adjusting to learner rates.
If you make the learning rate bigger, you might just become unstable.
Yeah. Like if I make the learning rate smaller, then this won't happen. So
It's better to. It's often better to keep the learning rate and increase the momentum.
And another question: which one is the constant here? I couldn't find it. Which one? Was
Oh, the constant I was talking about. Oh, I think I might have been talking about lambda.
no, from this equation.
Oh, yes. The constant. Right. I didn't want to write it all out, but it's on the previous slide. So you get a constant from here, which is log of 2 pi and log of sigma, and then you get log of 2 pi and log of sigma 0.
Okay.
That's okay.
Yeah. Because it's all mathematical. So can I say that this forward scale divergence is more likely to find the opposite of the other distribution?
It finds the forward scale divergence finds a kind of spread out distribution that covers all possibilities.
So it's spread out, not.
This is the thing that this Q is the thing that minimizes the.
So if Q is let me see, if PZ is like only half of it, so what will QZ look like?
Oh yeah, no. Here PZ is bimodal.
Yeah.
So if PZ is just this bit, then Q will definitely move over to match it.
Move over to match it. Oh, okay. And so,
But if P is bimodal, Q will spread out to try to cover both modes.
okay, so if PZ is another Gaussian, like only one peak, so what's the
If P is unimodal, then Q will be a gap. Q will try to fit that one mode.
How's reverse gonna?
It'll have the same will happen. Yeah. So the interesting stuff happens when it's multimodal. Yeah.
Okay. That's probably all the question. Thank you.
Sure.
Well, excuse me. So in this case,
Yep.
why this delta W will work in this way? I think if we can keep the learning rate a bit smaller, it should go into the center and it's just in the center.
It would, but if the learning rate was smaller, it would still oscillate, but just smaller oscillations. It would.
Because it's a bit weird.
If the learning rate is smaller, it would still do the same thing, but just
so it will always behave this way.
That's right, unless we have the momentum. Yeah.
So will it finally converge? I mean, will this gap be smaller and smaller later, or it will always be the same gap?
If there's no momentum, it'll always be the same, like this.
It will
I think.
always be the same.
That's right, because it's to do with the geometry. It's to do with the geometry of the space. Yeah. I think.
I just have a question. In the space, do you usually use this when the cost function to state space is in 3D for the functions which are in 3D? Because as it is 2D, you've gone another direction to get it down to the global minimum. Is it only applied to the 3D cases, the momentum, or?
You can apply it in any number of dimensions, I think.
Okay, because I view it as in a 3D because you've added another dimension, so I was a bit confused in say.
Oh, it has to be at least 3 dimensions.
Okay.
Yeah.
Okay. Thank you. That was it.
Yeah, I have a question about maximum likelihood. Where is it? Things here.
Yeah.
what are we actually maximizing? Because I saw the distribution of likelihood is always of probability is also 1. So what are we actually maximizing?
We're maximizing the conditional probability of the observed data given the network weights.
So you draw something like this.
Yeah.
I should draw like
So
bell shape.
we assume that the red line is the underlying process, and that the deviations from the red line are caused by noise.
Deviation of red lines.
Well, we assume that this cross is not, the reason this cross is not exactly on the line is because of some noise.
Yeah, that's right.
So what's the likelihood of that amount of noise? Yeah. If the line is like this, then there would have to be a lot of noise, so that's unlikely.
Yeah, that's right.
Would be unlikely, but if the line is like this, there's only a small amount of noise, so that's more likely.
I think we're trying to reduce the standard deviation in that case. The lesser the standard deviation, the better the line goes through. Is it that
kind of? I mean,
is that the conclusion?
Actually,
it's like.
I mean, the simpler line.
You're trying to minimize the number of standard deviations.
Yeah, number of standard deviations.
Number of standard deviation of all data.
That's right.
Or a single point.
All of them.
All of them.
Yeah, yeah.
And yeah, also another question. Yeah, also about this momentum. I kind of don't understand what's the difference between how do you actually apply this to a gradient descent?
Well,
I don't quite get it.
This is
it's like
last time I taught the course, I had this is like alpha delta W plus 1 minus alpha times dE by dW. Which maybe was a bit easier to understand.
Yeah, it's just,
but it doesn't. But it's different from what's in the textbook.
If you put this here, it's the gradient descent. It's a modified form of.
What are we actually using? Is this one?
Well, yeah. So delta W is like an approximation to the gradient, but it's a weighted. It's like an average of the gradient over a period of time, and it's multiplied by it's an average of the gradient over a period of time, but it's multiplied by 1 over alpha. Well, it's multiplied by 1 over 1 minus alpha. That's what makes it conceptually confusing.
Yes.
But the thing is,
if we are really using that, we'll just come up with 1 delta and using this equation.
That's right.
That sounds like
the problem is, like I say, like when I had alpha times this plus 1 minus alpha times that, you could definitely tell that it's a weighted average. But the problem, I think, the reason the problem with that is, if you formulate it in that way, when you increase the momentum, you have to also increase the learning rate. So the reason they write it this way is because they want to make it independent. You can change the momentum without changing the learning rate. So that's why they do it this way. So basically, this is.